Good evening, ladies and gentlemen. My name is Henry Garcia. I'm a member of the Energy Institute, and I'm also part of the London Branch Committee. And I would like to welcome you to the second episode of our webinar series, Energy Systems and Digital Technologies. I hope you're all safe and, well, luckily we're out of lockdown now, so we can have more freedom, and eventually at some point we might come back to these events in a face-to-face format, which is actually more enjoyable. Nonetheless, I mean, it's also good to exchange ideas, and the purpose of this webinar series is to learn how digital technologies can help to raise the bar in operations in almost all areas of the energy system: oil and gas, wind power, methane reduction, battery storage, hydrogen, carbon capture, usage and storage, and integrated networks. And today we have two special guests who will share their experience with us, Marius Voss and Jonathan Bosch. Welcome to the Energy Institute. And they will both share a 20-minute presentation followed by questions and answers. Please submit your questions to the Q&A panel as you listen to the talks. All right, so let's get started with our first guest, Marius Voss. Marius is heading up the Global Energy System Group at Rystad Energy, focusing on the energy transition and holistic energy system modeling. He moved to this position quite recently, having been the advisory arm of Rystad for the past 6 years, focusing on the entire energy space. And the title of his presentation is Digital Technologies Enabling the Energy Transition. Please, Marius.
Thanks. So I'm going to, first I thought I'll give a quick introduction to Rystad Energy for those of you who don't know us and maybe don't know everything about us. And then I'll go through how we see, or kind of the core topics of the energy transition and digitalization related to that. And as Henry said, I'm just recently transferred to this position, heading up our global energy system, but I've been working with more or less the say similar tasks and strategies, but within the consultancy arm of Rystad Energy. So with that, quick highlights of the company. We're now about 300 employees, headquartered in Oslo, Norway, offices around the globe, with maybe core hubs out of Houston, Singapore and London outside of Oslo. And then we are kind of spreading out throughout the entire energy system in terms of our coverage. But that being said, our heritage is basically this: our first kind of database product that we launched almost 15 years ago, which is an upstream oil and gas database covering all fields globally with reserves, production profiles, economics, investments, and so on. So that's where we're coming from as a company, but in the past 5 years, we slowly transitioned with the rest of the industry, I guess, towards the wider energy space. And today we cover kind of the same as you see here. We used our heritage, our bottom-up approach, covering the entire oil and gas system, and then transferred that into the other parts of the energy system. So, for example, we have a similar database for wind, with all wind farms globally. Actually, in Europe, it's down to the turbine level. For solar, we have a similar setup with all solar farms globally, and then obviously green hydrogen and grid storage to support that. So we have all the capacity and the infrastructure that these projects are tied into. That's the status quo of the energy system, I guess. And then we are also embracing the transition and going into all the parts of the energy system. So our products in the pipeline that are soon to come is all power plants, not only the renewable plants, expanding into global coverage of all power producing assets, and then also into the industrial sector, covering more focusing on the demand side, and eventually also the emission side of the industrial sector, so that we're able to capture both the energy demand and the emissions coming from these facilities. And by the way, we also either based on reporting or modeling forecast emissions from the entire upstream sector as well. So field by field emissions data, which is great tool for a lot of our clients in terms of benchmarking themselves on their performance and so on. And then expanding into CCS and blue hydrogen. It's kind of an obvious extension of what we're doing today. Battery manufacturing is also extremely important going forward to understand. And a global emissions database is also what we're aiming for in the end. Probably a year or a year and a half away, but that's kind of the end state that we're working towards today, is to understand the entire energy space, all production, supply, demand of energy, asset by asset, and also on the other side of the balance, and understanding the entire demand for energy, and also the emissions related to that. Okay, so that's the short summary of Rest of Energy, and then going over to the energy system and the transitioning of the global energy system. And digital has been a big buzzword for several years in the oil and gas industry, which we originate from. Is, I guess, digitalization have been on everyone's lips for I don't know, at least 10-15 years, but it hasn't really picked up and happened before quite recently. And the reason for that is that to be able to utilize kind of the digitalization fully in especially the heavier industries and in the oil and gas industry, for example, where complex industries, you need certain criteria. Obviously, you need data storage. That has been around for a while, but it continues to become cheaper and cheaper. Data processing has also increased exponentially and is now extremely cheap compared to what it was 5 years ago. Sensors is kind of not necessarily a new thing, but it's newer, and that as well is becoming extremely cheap and being placed on more or less all equipment. All possible use cases for sensors are today installed, and it has rather been the ability to utilize and understand the sensoring and the data coming from the sensors rather than the actual data feed itself. And then lastly, connectivity. That has been an issue, especially for remote locations. That is quite normal for the oil and gas industry, which is also becoming cheaper and making the digitalization 2.0, as we call it, possible in the energy space. Okay, so that's a bit of background, and then I'll go into the global energy system, how we define it. So the red part is kind of the legacy of the energy sector with the fossil fuels. Coal, oil, natural gas still making up 75% of global energy, or if not more. And then how everything trickles from primary energy to the left, meaning the production, the upstream part of this energy industry, and over to final demand to the right, normally separated into these sectors with buildings, vehicles or transportation, and then industry as different core consumers of energy. And obviously there's a lot of digitalization potential across the board here, and I've picked I picked some topics that I wanted to go a bit deeper into. Obviously, it's limited time today, but I'll touch upon the ones that you see here, and our take on those. So starting with legacy, digital oil fields. It's kind of the buzzword that is being used for digitalizing the upstream sector. It applies to gas fields as well. And industrial data platforms, that's something that is applicable to industry, obviously, but also the oil and gas value chain. And most of the initiatives within the industrial data platforms has actually grown out of the upstream industry because of the sheer complexity. And that complexity is obviously present in the industrial sector as well, a bit dependent on the sector. So I brought an example from a study that we did for a client on digitalization within oil and gas, looking at value creation potential from different digital initiatives. And the first one is maybe obvious, and it's not necessarily revolutionizing, but you would be surprised of how many companies, both within oil and gas and within industry and refinery and so on, that they don't really have a structured way of handle their data. And it's not in terms of coordinating data, but it's just a matter of getting access to data. So that's one of the major initiatives that are going on across most of the major oil companies today, is to structure data in a better way, visualize the data, and be able to kind of understand the data and get access to it, basically. Because you have all these different disciplines and silos that are sitting apart from each other and don't have access to or don't know that some kind of data or analytics exist in the company. And then as you move to the right, the complexity of the digitalization effort becomes or increases, but the value creation also increases. But in order to take the low-hanging value creation first, then it's normal to start with data visualization. Advanced analytics is more in terms of utilizing the data in more predictive manner. So you use the data that you have, you feed that into a system where that can be used to give predictions of, for example, maintenance schedules and so on. Yeah. And then if we look on the top part of the energy system, the kind of the where we need to go in order to transition away from fossil fuels, and the disruptive elements in there. If we start from the left with virtual power plants, I guess you're familiar with the concept, but it's an efficient way to coordinate across several renewable assets. So, for example, Statkraft, Norwegian major power producer, they were among the first globally, if not the first, to develop the first commercial virtual power plant, and which is now basically Europe's largest power plant. 100% renewable, have the capacity installed of 10 gigawatts in kind of this single virtual power plant. And that means that they control all the various assets tied into that power plant, all the wind turbines, all the solar power plants and hydro plants, and are able to coordinate how they produce and when they produce across this. And what's so interesting with this, if you, in addition to this, combine this with storage in some way, obviously Statkraft have access to a lot of hydropower, which is a bit special, but combine that with battery grid storage instead, you give the operator much more wiggle room in terms of getting more value, more revenue from the power generation. For example, especially solar is hit hard when the sun is shining and everyone is producing electricity at the same time. Then obviously the power price goes down, and then the realized power price is not as high as it could be have you been able to shift the generation to a different point in time. Another big revolution that everyone is familiar with, I guess, electric vehicles. It's something that is on the verge of becoming a disruption. The technology is more or less ready, but it's probably the spearhead, I would say, technology-wise, in the entire energy transition. And the main problem was that 60% of all demand is from transportation. How do you decarbonize that? So I guess Tesla did the right in attacking that problem first, given that their ambition is to accelerate the transition to sustainable fuels. And within that space, there's basically 4 major digital initiatives or technologies that are being or have been developed, which is the power management system, making it able or making the vehicle able to actually run on batteries and drain their batteries in an efficient manner. It's automation of manufacturing, which really isn't a new thing, but the players within these newcomers within electric transportation have really revolutionized this and taken it a step further than legacy auto has. So that's not necessarily a revolution by itself, but it's a great incremental step in making production and manufacturing more efficient and reducing costs and making the cars more competitive towards internal combustion engine cars. The third is autonomy, which is still not proven. There's a lot of doubters in the society, including internally at Rise of Energy, but it's a typical lunch topic of ours. It's happening fast, and it's just on the verge of kind of proving itself. There are several candidates, and I guess the 2 that are furthest ahead are Waymo and Tesla, and they are both at the verge of displaying that this is possible. Maybe not this year, but in a very near future. And then lastly, the digital experience, making the new kind of the software and the interface in these new vehicles superior to the existing alternatives. And that doesn't necessarily need to be specific for electric, but given that they are building everything from scratch, it's much easier for them to implement a much better digital experience than it is for the traditional automakers, because they already have their contracts with the suppliers and so on, and on the different equipment doesn't necessarily communicate that well and are not able to tie that all that into one common data platform. Just on some data on the adaptation of electric vehicles. In Norway, we've kind of seen this in the making for a long time, given that we have had incentives and subsidies making electric vehicles basically at cost parity compared to internal combustion engine cars for several years. But what's interesting, and I think is a good illustration, is this is what happened in Norway with cost parity. We expect cost parity to happen in a couple of years, which means that the cars or the customers don't really care whether they buy an electric vehicle or an internal combustion engine vehicle from an economical perspective. And that development that we've seen in Norway has happened during a period with extremely scarce selection of models, while in the coming 2 years it's going to be an explosion of potential models that you can buy. And we're also already seeing the effect of this especially in Europe with explosion in 2020 in terms of adoption rates, especially France, UK, Germany are ramping up quickly. China has been slowing down, but that's a different story because they have been in the past quite aggressive on subsidies, and they have kept substantially back on those subsidies of the last couple of years. But we expect that to kind of accelerate again once these vehicles become at parity with the fossil alternatives. Yeah, and I also included how the global average is projecting or progressing. We're now at 4% actually globally. And lastly, and I think these three are all maybe a bit intertwined. Smart grids is kind of a overarching theme covering everything that is smart in some way in the grid. That could be virtual power plants. It could be better and smarter storage or frequency control in the grid, or it's smart buildings with demand response. And I guess Jonathan in a minute will talk more about that. But this is the main focus on the demand side, I guess, is how to better focus or shift demand in an efficient way, and that is you can come a long way with efficient pricing of the electricity and meters that are able to capture the consumption of power at a given time, so that you pay the price at the same time as you use electricity. It's maybe not as relevant for you and me in our homes, but makes a lot of sense for larger companies that are able to shift their consumption in a certain direction to do that. Digital storage is also something that is picking up very rapidly now, with several big use cases of battery storage, basically disrupting the existing frequency control markets in which they enter. I guess you've heard about the big Tesla battery in Australia, Hornsdale Power Reserve, where after introducing that battery pack supporting the frequency control market, only taking a very marginal or adding a marginal share of capacity, it decimated that market overnight, removing about 96% of the value from the existing utilities in that market. So that was a quick summary in terms of how we see the future. I think the battle is still a bit open, at least between hydrogen, batteries, and CCS as kind of competing technologies. CCS obviously with the aim of sustaining or prolonging the fossil fuel era. Hydrogen has been on the agenda for quite some years, so that there were IEA symposium on hydrogen back in the 70s, and I think that's revisited that topic quite frequently, but it hasn't really picked up. It's starting to do so now, but we see the progression in the battery technology and the cost of batteries to be so rapid that we believe that batteries will continue to take a larger and larger share of the future energy system. Yep, that was my 20 minutes, I guess.
Thank you, Marius. It was a very, very good presentation, very informative. We have 27 attendees, and we have a couple of questions for you. The first question, I think, is a challenging one. In your opinion, what is the key technology that will accelerate the energy transition?
The key technology?
Yeah.
A good question. I would, the obvious answer is given my presentation just now with batteries and the development of batteries. But in terms of if we focus more digital, I think a lot of these energy forecasters and our peers are underestimating the potential in autonomy, because I wouldn't expect many autonomous fossil-fueled cars. Basically, it's easier to do that with electric vehicles because of the entire powertrain. It's easier, and that is potentially going to disrupt the entire transportation sector and the transportation system in a sense. One thing is that you don't really need your own car. And what does that mean? That the ownership cost or the cost of using a car will go down significantly, which means that potentially people will, to a large extent, stop or at least buy fewer cars. And the cars that will be bought either by private persons or by these new autonomous fleet operators will be electric, and hence the electric part will take an increasing share of the mileage driven, not only of the vehicle sold, but also of the mileage that is being driven, and that is kind of a double hit to oil demand. And I guess also the one that is not necessarily most difficult to abate, but it's a difficult one because you have all of these smaller emission sources compared to larger power stations or industries.
Okay. Yeah, we have other couple of questions. Is Rystad Renewable Cube database an example of an industrial data platform?
No, I wouldn't say so. An industrial data platform is basically it's also something that's being called a digital twin in certain occasions. It's kind of a way to structure the data, and whether that data represents a digital version or a copy of the reality, or if it's just a way to store data. It's up to the user to define, but that's kind of the main application of the industrial data platforms. While the Renewable Cube is, you could say it's an industrial data platform of the entire renewable energy system, if you were to draw it to the extreme. But it's a database containing all renewable assets globally. That being said, obviously we don't have access to the actual power generation and the actual state of some equipment on these power plants. But we, based on weather statistics, reporting, and so on, we get access to some. So then we know the capacity, installed capacity, and then we model the generation in terms of forecasting. And then when there is generation data available from governmental sources and so on, then we obviously feed that into our system.
Okay, and the last question we have is, how do you see the deployment of battery storage in Norway?
In Norway, I think in terms of grid storage in Norway, it would predominantly be for supporting distribution grids when electrification. We have 60-70% share of sales being electric vehicles today, but we're still just at 30% or something of the fleet, and that 30% is very much skewed towards the bigger cities, which means that when the more rural areas become or adopt electrification of the transportation sector, you would need distributed batteries in these smaller parts of the grid. But on a larger scale, in terms of sustaining variations in renewable energy. We don't really need that in Norway, given the hydropower that we have, which is basically is our grid storage. But I know that, for example, in Germany, it's already a big market and a lot of renewables, obviously, and negative electricity prices at certain occasions, and there they have built out so much grid storage that they are actually now the frequency control market that was being disrupted in Australia. There it has come so far that the batteries have already disrupted their own business model because there's basically too many batteries, so not much to compete on anymore.
Okay, well, thank you very much, Marius. Very interesting presentation and very interesting questions as well. Now let's continue with our second guest, Jonathan Bosch. Jonathan is currently a data scientist at Open Energy, where he contributes at all levels of product design and development, including designing algorithms for the operation of grid-connected distributed assets that are exposed to flexibility markets. And the title of his presentation is Automatically Optimizing and Trading Electricity from Low Carbon Technologies with Dynamic Demand 2.0. Welcome, Jonathan. Jonathan, you are probably muted. Jonathan, I think you're muted. Could you please unmute yourself?
You can hear me now?
Yes, I can hear you now. Welcome, Jonathan.
And thank you very much. I think we have also, did you see there was my screen has everything you can see, or is there a mark at the top?
There is a mark at the top, but it minimizes when you start the presentation mode.
Okay, we'll go with it because I think it might be to do with the platform. Okay, thank you very much. And Marius, thank you for setting me up quite nicely with talking about flexibility and batteries just at the end of your presentation. Very interesting about digitalization. So as Henry has introduced me, thank you very much. I'm a data scientist from Open Energy, and I'm going to talk about optimizing and trading energy from low carbon technologies, so including batteries, and so taking opportunity from flexible markets in the UK. So as you mentioned, Marius, we're going through a transformation in the energy system from a fossil fuel and centralized analog one to a more decentralized, decarbonized, and digital. And this is kind of a system that's more reliant on data. So it's important to create data platforms that can enable this. So to enable increasing share of distributed renewable energy, we're going to need more flexibility in order to balance the supply and demand on the grid. So Open Energy, I guess I can just give you a quick overview of what we do before I go into the details. So we're using kind of a data machine learning approach on a cloud-based platform to automatically optimize the dispatch of flexible assets, such as energy storage, with batteries, demand-side response, and also things like electric vehicles. And so this optimization is according to the system needs, market signals, and also, in particular, the asset requirements. So I'll talk through our platform, which is called Dynamic Demand 2.0. So that's in the title that you can see on the website, which does the optimizing and trading power from these technologies. And the next button. And also I'll give you a little bit of a background on flexibility markets so that you can recognize the opportunities for these new flexible technologies. So fundamental to this is kind of our generation, changing generation mix. So quite simply, this is quite a good figure to show just how quickly, just how rapidly the UK electricity system has been changing in recent years. So this is just looking at between 2019 and 2020. We also have to consider that the National Grid ESO operator has announced it will be fully zero carbon by 2025, which is quite soon. And as you can see there, the biggest, I guess, surprise, or when people expected it, is that renewable share is growing extremely fast. This is enabling carbon intensity to reduce, and also we have electricity demand falling, and that's kind of accentuated in kind of the current climate with lockdowns and pandemic response and stuff like this. So this has presented a much bigger challenge in balancing the grid due to all of these things. And also we have things like the inertia problem on the grid, where growing renewables on the grid has become a problem. So gas peakers are at the moment crucial to dealing with low inertia, but the cost is driven by commodity costs and operational costs during short dispatches at the peak period. But the bottom line here is that the cost of balancing is increasing for National Grid. So there's a huge opportunity for flexible system, flexible assets. And if we look at this slide, we can see the benefit of the cost of battery cells has been going down, and in 2025 to 2030, it'll be below $100 per kilowatt hour. And in the past year, and if we look at the growth of battery flexibility, we've had 164 megawatts of new storage capacity, and that's predominantly batteries, with most connected to the distribution networks. So electricity storage is co-located with wind and solar often, and so this actually also supports a business case for a range of revenue streams. So take advantage of price arbitrage and also balancing the balancing market and other grid services. So how to enable these flexible assets to deal with renewable intermittency and balancing the system is crucial in the immediate future, basically. So just a quick overview of the market landscape here. I think there's a grey square at the top of that, but it just says it's just flexibility markets. So basically, this is just to emphasize that we have a very complex and changing landscape for flexibility. It's kind of divided at the top into grid services, distribution services, and then arbitrage opportunities are also driven by electricity cost variation throughout the day. The principle here is that assets or flexible assets can be paid for generating, and they can be paid for shifting demand. So that's demand side response. If we dive into that, you can see that Ancillary Services, FFR, has presented a lucrative grid service in previous years, but in recent years the price has crashed, and that's mainly due to more entrants into the market. So looking at the distribution network, DNO services are more localized, and the opportunity there lies in the locality of those assets and how to distribute or shift that electricity. Arbitrage, basically the opportunity for arbitrage is that electricity is priced differently at different parts of the day, and we have a wide landscape of opportunities in the flexibility markets, and they're changing all the time. So you can see the frequency down at the bottom. There's lots of frequency services that have historically been provided by grid, but now balancing mechanism, which is over on the left side, is becoming more and more important for batteries. And so here, just a few of the important ways that we can use the flexibility markets. But we should emphasize that 90% of, or more, I think more than 90% of electricity volume is actually traded before gate closure. So gate closure 1 hour before real-time electricity dispatch. But the rest of that volume can be attributed to flexibility markets. And so after that gate closure, National Grid will take actions on the balancing mechanism to ensure supply and demand is met, and that's in the order of a volume of 1 gigawatt. And this is also the conventional way that National Grid has balanced the system, historically using bigger centralized generators like thermal and hydro. Fast frequency response, which is the top one there, has been the main flexibility market opportunity for open energy historically. And we've usually, and the system generally works with tendering monthly to provide availability, power availability, if it's needed, to grid. And that's specifically when you're tracking the grid frequency in order to keep a frequency within contracted bands for National Grid. But other arbitrage opportunities include triads, so just under the balancing mechanism there, where the National Grid has implemented a high price penalty for power consumption during the 3 settlement periods in the winter season with the higher system demand. And they're settled after the fact, so we don't know them in advance. So that means triad prediction is does play a large role in the dispatch of flexible assets during the winter season, where price penalties or the potential revenues for exporting power during those periods can be extremely lucrative. By optimizing flexible asset dispatch on a specific site, you can also generate forecasts for site demand and weather, etc. So that shifting asset dispatch, we can offset the demand and prevent the exceedance of import, things like import and export limits, to maximize the benefit of site demand, and also of potential solar energy on site. So just looking specifically at the ancillary services, we can look at, so up here I've put a grid frequency event that happened on August the 9th this year. And it shows that grid frequency fell below contracted boundaries, and that was due to over a gigawatt of generation falling out of, or going offline, and also another 350 megawatts of embedded generation was disconnected. And so the UK experienced blackouts across that period. With flexible or with frequency response, the asset tracks and reacts to instantaneous grid frequency changes to ensure that National Grid meets its license obligation to keep grid frequency within 1% deviation from 50 hertz. So in that sort of situation, flexible assets that do fast frequency response will be the first types of assets to react to a low frequency event. So obviously, when frequency falls outside of the deviation, a high frequency is indicating an overgeneration of power plants or an underconsumption relative to the forecast demand, and therefore flexible assets will draw power out of the grid, and the same vice versa. And as I said earlier, FFR has historically been tendered monthly, but now there are weekly auctions of fast static FFR and dynamic FFR, and this has increased market liquidity in the last year or so, which is adding optionality to the crowded monthly render rounds, which have had more and more assets into the market in the last few years. I'll go on to the next slide. There are also new opportunities such as dynamic containment, which is also a grid service. And as a result of grid events, such as in the last slide, dynamic containment is really aimed at a fast-acting post-fault regulation service, where there is only a small power response needed at small frequency deviations, but once frequency deviates outside 0.25 Hertz, there is assumed grid fault or generator fault, and the power response should be high. However, the barrier to this is the strict requirements for passing pre-qualification tests. So it requires a response time of less than a second and much higher real-time metering frequency. So it's clear that these kind of new services are aimed at large front-of-meter batteries, in the order of 50 megawatts, that sort of size. But at the moment, this service is still in its 6-month trial period, with less than, I think, 200 megawatts currently bidding into the system. However, the price is much higher than FFR at £17 per megawatt at the moment, which is about 3 times the price of FFR, which makes it a potentially lucrative market for response assets that can be controlled in a highly granular fashion. And you can also see here on the left side that the utilization compared to FFR is much lower because, in general, the higher frequency deviations happen much less frequently. And energy arbitrage is the other flexible opportunity. So basically, when energy storage, energy trading strategies where we aim to buy energy from the grid at a low price and sell it back when we have a meaningfully higher price. Arbitrage is also complicated by the introduction or entry of new grid services and the change in landscape of the energy markets. But during COVID, as I said earlier, the wholesale price has dropped a fair amount and has had basically an impact on arbitrage opportunities. And that's also as a general result of low volatility in energy markets. So on the bottom right graph, you can basically see that the opportunity cost is for arbitrage, general arbitrage actions is in contrast to grid service opportunities such as BM. But however, that's in addition, as more renewables are coming online and we have older plants retiring, we do expect much higher volatility in the kind of medium term. So flexible arbitrage opportunities should be growing in that time frame. So just a quick look at BM as well. So basically the balancing mechanism is the kind of new opportunity area. National Grid uses this to secure real-time flexibility to balance supply and demand on the system. And it also takes account of grid constraints, other grid constraints as well. So as I said earlier, it's traditionally been serviced by more centralized flexible assets such as hydro and thermo. But in the last year, I think the last 15 months, we have seen about 10 batteries or about 200 megawatts worth of grid-connected batteries registered as BM units. And so an example here is block switch battery, which shows the profile of charging and discharging throughout the day. Discharging represented as offers accepted, which is in blue, and charging red bids. So the opportunity in general is limited by being called by National Grid to charge, to dispatch or your asset. But the difference here is if we're using batteries in the balancing mechanism, we have to consider state of charge management so that we have sort of power availability is sufficient when there's a need to accept an offer or a bid, which is not generally the case with things like hydro, where the availability is fairly continuous throughout the day. But batteries will begin to play an important role as the trust from National Grid in batteries providing these services reliably is proven. And also, well, as new expertise, understanding the value of batteries and managing the state of charge is understood better. Another thing to consider is that warranties of batteries and these types of technologies have different expectations of battery cycling in BM compared to previous services that were popular, such as frequency response. So warranties of these assets might also change as we realize the potential in the balancing mechanism. So just a slide to show how the balancing mechanism offers. It generally mirrors the whole the energy market. So the blue line at the top is basically mirroring the volatility of wholesale prices in electricity. So in general, the revenues are revenues in BM are driven by the bid offer spread and utilization, and the offer price is obviously linked to the electricity price. But battery usage in the balancing mechanism is driven by requirements from National Grid in real time. But there are many reasons why this may be, but why the opportunities may be limited, including, as I said, with control room operators, there may be a lack of automation and experience with distributed flexibility. But as you can see on the right-hand side of the chart, we have increasing, or the bid price tends to go negative. So it's more variable and strongly linked to renewable generation, or wind generation. So we have high day-to-day variability in the price spreads, and there's a huge difference between a low wind and high wind days, and we get negative bid prices, meaning that the asset owner gets paid to consume electricity in that case. So we can see as wind penetration increases, we should see increasing instances of these negative prices, and we'll also see increasing volatility in the general flexibility market. So in general, BM is presenting a much a growing opportunity for batteries in general. So that's just a bit of a background on flexibility markets. But now let's have a little dig into dynamic demand 2.0, which is our optimizer algorithm at Open Energy. So as I said earlier, it's our cloud platform that automatically optimizes and dispatches flexible assets. And it also provides feedback to the asset owners through an API about what dispatch profiles the algorithm or dynamic demand 2.0 has sent to the asset. It's currently optimizing a wide variety of flexibility assets, and those include things like commercial cooling equipment, on-site generation such as combined heat and power, and also down to things like batteries I've already talked to, and also now electric vehicles. So the optimizer in general takes as inputs the market prices from stacked opportunities, so service contracts to day ahead and intraday price signals, and also market intelligence such as weather forecasts and system demand, so that the optimized daily asset dispatch can be amended and improved on an intraday basis, or the profile can be updated in near real-time basis. The optimizer also understands the physical constraints of different assets and the site types, and learns the demand profile of on-site energy demand in order to prioritize other site activities and maximize revenue opportunities. So the profile, the dispatch profile that the optimizer comes up with a half-hourly dispatch, which is amended in real time, that balances the trade-offs between opportunities with site and technology constraints, considering state of charge management of the system for batteries, and operating within the warranty limits of the technology as well, which may be defined on a different time range to the actual operation. So just for a little deeper dive before I show a couple of case studies. I think I still have a few minutes to go through those, but here we go. Here we can see that in general, the optimize we optimize and dispatch a variety of different asset types, and the strategy is broken into three categories. All cases across all types of assets, we include a scenario which deals with site-specific variables, import and export prices, site demand, forecast, and renewable generation, and also the commodity costs are included. So that's site-specific. On the model side, this is technology or asset-specific, so we have to define the type of flexible technology we're optimizing. So that can range from batteries or biogas CHPs, or even things like hydrogen electrolyzers. And in those cases, the control variables will be different and the constraints will generally be different. So the model defines the relationship in general between flexibility and power. So what is it possible to do given the given technology? Open Energy, we have a fairly asset-focused integration with our platform, which means that we respect the warranty and operational constraints of the asset as a priority. So, for example, that means our system will lose controllability of the asset, which means our command of the asset is automatically switched off. And that's built into the design of our system, so that the site operation and site demand is never impacted by our technology. On the solver, this is the one part that's common to all, and this is the math and optimization part. The objective here is to minimize the cost of dispatch while respecting, as I said, the constraints input by the scenario and the model. So just to have a look at a couple of examples of what Dynamic Demand 2.0 has done. So in this example, we have historic data, or like 1 day of data from a battery with site demand. So here you can see that we have an automated profile, which has used machine learning, where the optimized power is in blue and the state of charge is in green. In this example, the dispatch profile is optimized to respect site demand, which in this case is an electric vehicle charging site. Battery charges during the day. You can see where there is forecast availability and site demand, but mostly the charging is done at night when it doesn't interrupt with site demand. We're also stacking services here. So we have grid services, which is FFR, and price arbitrage going on at the same time. And so the optimization stacks those services simultaneously. So the battery dispatch during the day is basically dominated when the green line on the left goes down. That's a huge discharge during peak period, and that's a triad peak price signal, where we have a prediction algorithm to find the most likely settlement period to be a triad, and we want to discharge there. And in this case, since the FFR tender, which is shown by the dotted purple line in the bottom right graph ends at 3 p.m. We also have some extra charging just pre-peak so that we can discharge maximally for the triad period. This example is looking at a battery site with solar generation, and as you can see here, the difference is that we have now solar being generated during the day. It's a factory site and with rooftop solar. The optimized profile is driven by basically the solar generation. The site is constrained to minimize the battery export when the site demand can be delivered by on-site solar. So we maximize the solar generation, the use of solar generation during the day. So in this case, the battery charging is done mostly during the day when solar is highest, as opposed to nighttime. Again, the battery tries to dispatch during a triad period, and the price signal is highest. However, we don't. In this case, there is no site export going on, since site demand is high at this point, and it is therefore more valuable to reduce the import to the site than an export to grid. So I'm just conscious of time. I only just looked at it. Maybe I skip this one and just show my conclusions there. So basically what we're talking about is maximizing flexibility from distributed assets. So from this point of view, it requires aggregation, technology platforms, and data transfer. And flexibility is pretty key here. So switching between grid services and arbitrage is going to be more and more important on a granular basis in order to maximize the value from flexibility markets. And now we're at a kind of period where new ancillary frequency markets and entry into the PM is going to be a significant opportunity in the flexibility markets from now on. And I guess I better finish. Sorry about that.
Well, thank you very much, Jonathan. That was very insightful. Maybe we have a time for a very quick question.
Okay.
So I have here, what type of assets are currently connected to Dynamic Demand 2.0?
What kind of assets? Okay, so we have quite a broad range of assets in general. The kind of emerging and biggest type are the kind of front of meter batteries, and but we also connect to CHP devices, electric vehicles and chargers. We have historically done a lot of demand side response, which includes water pumps on water industrial sites, as well as things like tar producing machines. I forget the name of them, where temperature has to be controlled. So this is why I was saying earlier about they're called bitumen tanks. And we also used heating and cooling machines in supermarkets as a historical project, and we have also quite recently connected to hydrogen electrolyzers. So in the case of electrolyzers, the control variable you're looking at there is generally the gas pressure inside the hydrogen gas bag, so that you can optimize when you're using grid power and when you can have flexibility. And we also, I think there's also vanadium flow batteries, which are kind of almost like a battery technology, but slightly different. I think that's as many technologies I can think of.
Well, thank you very much. I really enjoyed the both presentations, and we're now reaching the end of the webinar. And I want to thank again Jonathan and Marius for sharing your experience with us. We had around 27 attendees in this webinar, and thank you to you all for your participation.